It's actually built like a core that's like a tower, and then each step is made of accretions, like the skins of an onion leaning against it.
Picture a hole in the ground, 7 meters wide on every side, cut straight down through solid bedrock for 30 meters, ending in a chamber of granite sealed with plugs so heavy it would take modern machinery to move them. For 200 years, every archaeologist who has stood at the lip of that shaft has called it the same thing: a grave. And in August of 2024, a small team of engineers looked at the numbers behind that grave and said the geometry does not match a tomb at all. It matches a machine. This is the story of the Step Pyramid of Djoser, the oldest large stone monument on Earth, and the paper that tried to rewrite what it was actually for. To understand why that claim landed as hard as it did, you have to understand what the Step Pyramid represents in the history of human building. It rises on the Saqqara Plateau, south of modern Cairo, constructed around 2670 BC for a king of Egypt's third dynasty named Djoser. 6 enormous tiers of dressed stone climb more than 60 meters into the sky. When it was finished, it was the tallest structure any human being had ever built, anywhere on the planet, in any civilization, at any point in recorded history up to that moment. That alone would make it remarkable. What makes it strange is what came immediately before it. Before Djoser, Egyptian kings were buried beneath low, flat structures of mud brick called mastabas, barely taller than a garden wall. They were fine monuments for a village. They were invisible by the standard of an empire. And then, within a single reign, the record does not creep upward. It jumps. The Step Pyramid arrives already carrying 2 innovations that had never existed before anywhere in the archaeological record: the pyramid form itself, and the first large-scale use of fully quarried, precisely dressed stone blocks stacked with real engineering accuracy. Millions of stones, shaped and set by people who, as far as we can tell, had never built anything like it before. There is no field of failed test pyramids buried in the sand nearby. No half-collapsed early attempts where the mistakes were made and corrected. The record shows no learning curve. It shows an arrival, fully formed. The man credited with the design was named Imhotep, and the fact that we even know his name is itself extraordinary, since Egyptian architects were rarely recorded at all. Imhotep was so revered for what happened at Saqqara that centuries after his death, the Egyptians stopped remembering him as a builder and started worshipping him as a god of medicine, wisdom, and knowledge. That kind of reverence does not usually attach itself to a man who simply directed a large labor crew. It attaches itself to someone who solved a problem nobody else had solved. And the problem is a simple one to state and a hard one to answer. How does a civilization that has never stacked cut stone above head height suddenly do it at 60 meters, on a first attempt, without a single documented failure behind it? For most of the 20th and 21st centuries, the working answer has been ramps. Earthen ramps, timber sledges, rope, teams of laborers hauling stone upward under organized supervision, possibly with water poured onto sand to reduce friction. This remains the mainstream explanation, and it may well be substantially correct. But it has always had a soft spot in the middle of it, right where the specifics of vertical lifting at scale should be. Nobody has ever found the ramp. Nobody has ever found debris fields large enough to account for a ramp capable of reaching 60 meters. That absence has been patched over with assumption for a very long time. In August 2024, a team led by Xavier Landreau, a researcher affiliated with the Paleotechnic Research Institute in Paris, published a study that approached the site differently. Instead of starting with pottery, inscriptions, or comparative tomb architecture, the way Egyptology traditionally does, they started with satellite radar imagery and hydrological mapping, tracing where water would have moved across the Saqqara Plateau roughly 4,500 years ago. They were not asking what a structure meant. They were asking what it did. The first thing their mapping pointed at was not inside the pyramid complex at all. It was half a kilometer to the west, a massive rectangular enclosure of rough stone that archaeologists have known about for more than a century and never fully explained. It is called the Djoser Elmuter. Its walls run for hundreds of meters. There is no temple inside it, no burial, no inscription. It is too enormous to be decorative and too plain to be ceremonial. and for generations the honest answer to what it was for amounted to a shrug dressed up in academic language. Landreau's team proposed that the Djoser Elmuter was a check dam, built to intercept water and sediment flowing down from higher ground to the west. That claim only makes sense once you understand the climate of the period, and this is the detail that quietly reorganizes the entire picture. Around 2670 BC, North Africa was in the closing phase of what climatologists call the African humid period, popularly known as the Green Sahara. The region that is now the driest desert on the planet still had real seasonal rainfall, real vegetation, and real watercourses running across ground that is bone-dry today. Saqqara sat close enough to that transition to still receive runoff from an ancient drainage channel to the west, one that no longer exists in any visible form. The desert image most of us carry in our heads, endless dunes and blinding sun with no water anywhere, is simply the wrong picture for this specific moment in Egyptian history. If that dam is real, it explains something that has never fit comfortably with the ramp narrative. Landreau made an observation about the era that quietly flips the standard assumption. Before Egypt's later dynasties, he suggested, the builders at Saqqara likely had more trouble with sudden floods than with any shortage of water. Seasonal runoff arriving fast and heavy from higher ground would have needed to be caught and controlled, not conserved. A stone barrier sitting directly in the path of that flow is not a mystery under that light. It is the most predictable structure a competent society builds when water arrives in surges rather than in a trickle. On its own, that would be interesting but not extraordinary. Egyptians managed water constantly, through irrigation canals and basin agriculture tied to the Nile's flood calendar. A dam would be unremarkable from a culture already fluent in moving water across fields. The second structure the study points to is where the story stops resembling ordinary irrigation. Wrapped around the entire Djoser complex, cut down into the bedrock, is a feature known as the dry moat, a deep trench enclosing the pyramid and its courtyards along the full perimeter of the site. For most of its length, it behaves like a simple ditch. But in its southern section, it does something that has never had a satisfying explanation. It stops being one continuous trench and becomes a sequence of separate compartments, cut one after another in a precise row. The interpretations offered for this over the decades have included storage, quarrying activity, and ritual function, which is often the word archaeology reaches for when a genuine explanation has gone missing. The engineers looked at that same row of compartments and recognized something immediately, because the layout still exists today in modern infrastructure. It resembles a settling system, a series of retention basins used to clean turbulent water by slowing it down step by step. Picture floodwater entering the first compartment thick with suspended sediment, almost solid with grit, the daylight sitting on its surface rather than passing through it. As the water slows in that first basin, it loses its grip on the heaviest material, and coarse sand drops out and settles on the floor. The flow then spills into the next compartment thinner and less abrasive, where finer sand drifts out in turn. By the third or fourth basin the water has changed character entirely, lighter, clearer, carrying only the finest silt. By the final compartment in the row, there would have been standing water clean enough to see the floor beneath it. That distinction matters more than it sounds like it should, because grit is not simply dirt. Grit is an abrasive. Push a slurry of sand and clay into any mechanism built with fine tolerances and moving parts, and it scores surfaces, packs into gaps, jams anything sliding against anything else, and eventually seizes the whole assembly. Whoever cut that line of compartments into the bedrock understood, without a word of theory to explain it, that they did not simply want water. They wanted water with the abrasive removed. And that is not the reasoning of people who only needed drinking water or irrigation. That is the reasoning of people protecting something downstream that could not tolerate contamination, something with moving parts. Which brings the study to its most contested claim, the one that determines whether any of this matters. The shaft beneath the pyramid, the one that has been called a burial shaft for 2 centuries without serious challenge. Landreau's team compared its internal proportions against known Egyptian burial shafts elsewhere, measuring depth against width, wall finish, and internal features. According to their analysis, the geometry did not fit that pattern. It fit a different one entirely, matching the proportions of a cylinder designed to hold a rising column of water with a floating platform riding on its surface, the shape an engineer would arrive at if the goal was to lift something heavy in a straight vertical line without dragging it anywhere. The paper describes the theory in careful, restrained language, proposing that the internal architecture of the shaft is consistent with a hydraulic lift mechanism used to help raise building material during construction. To test whether the idea held up under real physical modeling rather than just visual comparison, the team built a full three-dimensional reconstruction of the site using commercial game engine software, layering satellite watershed data, old excavation plans, and the newly proposed dam and moat system into a single connected environment, above ground and below ground together, something that had reportedly never been attempted for this site before. Then they simulated the system running. In that reconstruction, water moves from the reservoir behind the dam, through the settling basins of the southern moat, dropping stage by stage from turbid to clear, and finally into a channel that carries it underground to the base of the shaft. There, a heavy platform filling the width of the shaft acts like a piston, and a limestone block resting on top of it is lifted not by human muscle pulling from above, but by the simple physical principle that water exerts upward force on anything floating on it equal to the weight of water it displaces. As the reservoir feeds the shaft, the platform rises through the dark, carrying the stone toward daylight, and when the water is released, it descends empty to be loaded again. The team modeled the force such a system could generate and arrived at a capacity in the range of 100 tons, an amount that, by their own account, is almost absurd for a civilization working only in copper, timber, and rope. But the researchers were honest about the largest hole in their own theory. No wooden platform, no float, no organic remains of any lifting mechanism have ever been recovered from that shaft. Timber rots. Plant fiber rots faster. After 4,500 years of flooding, robbery, and repeated excavation, nothing soft would be expected to survive, which means the absence of the object is not proof it never existed, but it does mean the central piece of the argument can only be described through the shape of the space it would have occupied, never held in a hand. The reaction from Egyptology arrived quickly, and it did not arrive gently. Julia Budka, an Egyptologist at Ludwig Maximilian University of Munich, raised a concern less about the physics and more about the room the theory was built in, noting that no Egyptologists were part of the authorship at all, only engineers and hydrologists reinterpreting a monument that specialists in the field had studied for 2 centuries. David Jeffries, a retired senior lecturer at University College London, called the idea ingenious and then declined it outright, saying the more widely accepted explanation, ramps and organized human labor, still holds. Others focused on the physical mechanics themselves, questioning whether occasional desert rainfall could ever supply a reliable water source across years of continuous construction, since seasonal rain is an event, not a dependable pipeline. And perhaps the sharpest objection of all came down to simple scale. The blocks in Djoser's pyramid are modest by later Egyptian standards, averaging around 300 kilograms each, well within the range that a handful of workers with ropes and levers could move without any machine at all. Building a dam, a filtration system, and a precision water lift to move stones that size, critics argued, would represent far more effort than simply carrying them by hand. And yet, strip away every disputed interpretation, and what remains is not nothing. The Djoser Elmuter is real stone in real ground, sitting exactly where a barrier would need to sit to catch runoff from the west, and it has never been given a fully satisfying explanation by anyone in over a century of study. The dry moat is real, cut into solid bedrock, and its southern section really does form a precise sequence of basins that resembles a settling system regardless of who built it or why. The 2 shafts are real, 7 meters wide, 30 meters deep, sealed at the bottom with granite hauled from hundreds of kilometers away for reasons no inscription ever explained. Even the researchers themselves were less absolute than the headlines that followed their publication suggested, stating plainly that traditional ramps and organized labor were very likely used as well, and that a hydraulic system, if it existed, may only have assisted the work rather than replaced it entirely. So even in the most conservative reading, something remains true that cannot simply be argued away. The people who raised the first pyramid on Earth read their landscape well enough to identify exactly where floodwater would strike, well enough to build a staged system capable of clearing suspended sediment out of it, and precise enough to cut 2 shafts 30 meters into solid rock with a straightness that still impresses trained engineers today. They did all of this at the very beginning of monumental architecture, with copper tools, rope, and human hands, and left behind no written manual to explain any of it. Whether that shaft beneath Djoser's pyramid was built to receive a king in death or to lift the stones of his monument toward the sky, the deeper truth sitting underneath the argument does not change. 4,500 years ago, on a plateau that is desert today and was not quite desert then, a small group of people solved an engineering problem so difficult that we are still arguing about how they did it. And maybe that unresolved argument is the more honest monument. Not a finished answer standing still in the sand, but a question still being asked, one generation of engineers and archaeologists at a time, at the edge of a hole that has been waiting in the dark since before most of history began.